So remember where we are. We're talking about you have some vector space, right? You have some vector space, and you've got and it's an abstract vector space, so there's no coordinates on it, right? You don't have a coordinate system like you do in Euclidean space. You say, I'd like to have a coordinate system on this, and so you realize that as long as you have a basis, then every vector is associated with a unique set of coordinates, right? That unique set of coordinates is the coefficients that you get from expressing the vector as a linear combination, right? That was our first thing we talked about last time, right? So putting a coordinate system on an abstract vector space. And then the second thing is the relation between two coordinate vectors, right? If you change the basis, well, you change the coordinate vector, right? And we saw that at least in Euclidean space, the way to get from one coordinate vector, the way to get change of coordinates is what we're talking about, change of coordinates. And to get from the coordinate vector with respect to one basis to the coordinate vector with respect to another basis, we saw that we needed some sort of change of basis matrix, right? We need to use the change of basis matrix. And what was the change of basis matrix? How do we get the change of basis matrix? Well, if you forget, we can always reconstruct it. You say, well, I know that if I have a vector and its coordinate vector with respect to b is this guy, that means that my vector in Rn, that means that my vector is this thing times B1, the matrix with whose columns are the basis elements, right? And on the other side, right, if I'm looking, I have something similar for U, for the other basis, right? And so what's the change of basis matrix to get from the B coordinate to the U coordinate? Well, to get to the U coordinate, right, we need to multiply this thing by the B basis matrix times the inverse of the times the inverse of the U basis matrix, right? And so this is our change of basis matrix. And so that's basically almost the whole thing we did last time, excluding the example. Okay. So today we're going to do something. So I regret that I have to do this to you, but the first thing we're going to do is pretty complicated. Okay. So get ready. So pay attention and get ready to think. Okay, so what we're going to do this time is something a little bit more abstract, which is change of basis in abstract vector spaces. So not just Euclidean space, but you right here we had Euclidean space, but now we're going to deal with an abstract vector space. Okay, and this is secretly the same thing, but it just looks more abstract. Okay. So like VB, a vector space. Okay, and suppose that the dimension of V is n. Let's say that you have two bases, E, which is W1 through Wn, and F, V1 through Vn. Okay, and these are both bases of V. Okay. just as before, whenever you have a vector, you can get a coordinate vector, right? So our question is, again, how do we get from the coordinate vector with respect to one basis to the coordinate vector with respect to the other? Okay, coordinates with respect to the w's, to coordinate vectors with respect to the f. Okay. Okay, and maybe I'll just sort of lay out what you need to do. Okay, so so we start off with the following observation. So observe, first off, that every wi can be expressed as a linear combination of the vi. Okay, so that's actually going to be the first thing that we need to do. We'll take every element of the basis we're starting off with, whose coordinate vector we're starting off with, and we'll express them in terms of the target basis. Okay. Okay, that's okay. Okay. So take elements of your original basis, right, these guys, and express them in terms of the target basis. Okay. Okay, so you say, okay, well, this guy can be expressed as S11 V1 plus S21 V2 plus da 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 plus Sn1 Vn W2 S12 V1 plus S22 V2 plus Sn2 Vn. Wn can be expressed as S1 V1 plus S2n V2 plus Sn Vn. Okay.
Why is that true?
Why can everybody be expressed in terms of the other guys?
Yeah.
Well, because this is a basis of your space,
Okay.
right? Right. And each of these guys is in the space.
Oh,
right?
they're both bases.
They're both bases,
I can
so
express
everybody
each
here can be
other.
expressed as in a linear combination of these guys, and vice versa. Right. Okay. Okay, so you notice that I wrote the indices backwards from what I normally write. Normally I write 1, 1, 1, 2, blah, 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 2, 1, 2, 2, blah, blah, blah. But this time I wrote them backwards. That's because what will happen is that it turns out that the matrix S, which is the transpose of that, so S11, S12, S1n, S21, S22, S2n, Sn1, Sn2, Snn, is the matrix we're looking for. That is, that this matrix will take coordinate vectors with respect to E and change them into coordinate vectors with respect to F. Okay, now that should be kind of mysterious. That should be extremely mysterious. We haven't explained that at all, right? I'm just saying this is what's going to happen. Okay, let me, so before I explain the method, let me just do an example to show you how you would use it. Okay. So here's an example. suppose you're in, so suppose your vector space is P3, right? Polynomials of degree less than 3. And your first basis is 1x squared. And your second basis is 1, 2x, 4x squared minus 2. Okay. So maybe take a minute and see if you can write down this thing here. Try to figure out what the S matrix would be based on what we just wrote. Find the matrix that goes from E to F.
The S is a scalar, each of those S's are scalar?
Yeah. Yeah.
Right,
So you just want to express this guy as a linear combination of those guys. Right, you express, well, I'll let you do it. Okay, talk with somebody nearby to say what you were doing or trying.
I was trying to write like the E values of each one of those S's. I was trying to write out
So I just realized I did this wrong because
something times 1 equals 1 times E then it has to be
But like, and then
plus 0 times
this was the 10. Specific It's like you want to
I don't know if we're allowed to use it. And then the next one, which is
So imagine
W2, which is X equals like
So this E is like
0
those
plus 1 half times 2X plus 0
So
times 4.
you want to find that matrix.
And then maybe for the next one.
Okay, who would like to say? Who would like to say what you got? Anybody? Molly?
I mean, I'll say, I don't know if it's right.
Sure, that's all right.
So I got a 3x3 matrix.
Yep.
The first row is 1, 0, negative 2. And 0, 2, 0. And 0, 0, 4.
Okay, that looks like you were going from F, you were expressing these guys in terms of these guys.
Yeah.
Right? But I actually want you to go the other way, express these guys in terms of these guys.
Okay.
Okay, but that's right for the early question.
Okay.
Okay, so yeah, so that's, you said, well, I'm going to take each of the elements of this guy, of this basis, and I'm going to express them as linear combinations of these guys. Well, 1 is certainly 1 of this guy, 0 of this guy, and 0 of this guy. So you take 1, 0, 0. Right, 2x is certainly 0 of this, 2 of this, and 0 of this, 0, 2, 0. This one is certainly negative 2 of this guy, 0, and 4 of that guy. right? So that's the perfect matrix to go in the opposite direction.
Wait,
right?
so if you say from E to F, that's going the other way?
Yeah. So going from, you're going to express the E guys. So what we want is the matrix that is going to take the E coordinates and express them in terms of the F coordinates. Okay. So what you gave is the one that's going to go the opposite way.
Okay.
Right. Yeah. So right, to go from E to F, you take the E guys, the W guys, and express them in terms of the V guys. Right. Probably you're thrown off by the fact that E is before F, but V is before W. Right. So I should change that at some point. Right. Yeah. Okay. So, but yeah, that's basically right. Your procedure was right. So let me just. What did anybody do it in the other order? Lizzie, yeah.
1, 0, negative 2.
That sounds like the same thing.
What?
Keep on going.
0, 1 half, 0.
Okay.
0, 0, 4.
0, 0, 4. I think that's not right. I mean, okay, so you say, okay, well, look, 1 is certainly 1 of this guy plus 0 of the second guy plus 0 of this guy, right? X is 0 of the first guy plus a half of the second guy plus 0 of the third guy, right? And then x squared, you're going to need a quarter of the last guy, right? To get that x squared, right? To get that x squared, you're going to need a quarter of the last guy. That gives you x squared minus a half. So you need plus a half here, right? Okay, so you did something wrong with the calculation, but you've got the right idea. Okay. Yeah, I think.
And then so then it's that
Then you take the
row becomes the.
Yeah, then you take the transpose of these guys. Okay, so your matrix is going to be 1, 0, 0, 0, 1 half, 0, 1 half, 0, 1 quarter. Okay, and I'm saying that, I'm saying without explanation yet, that this is the matrix that's going to go from the E coordinates to the F coordinates. Okay, so let me just give you an example. Let P of x be the polynomial 3 plus 2x plus 14x squared. Okay, and if I take P of x's coordinate vector with respect to E, what's P of x's coordinate vector with respect to E? Think for 10 seconds and then tell me. Five seconds is up. Go. Somebody tell me. What's P of x's coordinate vector with respect to E? Dan.
Going down the columns, 3, 0, 0, 0, 2, 0.
No. The coordinate vector of this, with respect to E, right? So to get the coordinate vector, remember, you have to express this guy as a linear combination of these guys, and then take the coefficients. Okay, the coordinate vector. You have a vector. How do you get its coordinate vector with respect to a basis? You express it as a linear combination of the basis, and then just use those coefficients. And so you don't get a matrix, you get a vector. A yoke, how about you? Do you not?
3, 2, and 14.
3, 2, 14. Right, just 3, 2, 14. So this is going to be 3, 2, 14. Okay. And if I said, give me the coordinate vector of this guy with respect to F, well, you'd have to realize it as a linear combination of these guys, and then give me the coefficients. Okay. Or you could use what we just did. So the coordinate vector of P with respect to F that's going to be, I claim that that's going to be S times 3 to 14. Right? Right? At least by my unexplained claim, S is the matrix that takes the coordinate vector with respect to the E basis and switches it to the F basis. If you work it out, it turns out to be 10, 1, 7 halves. Okay. And lo and behold, if you take 10 of 1 plus 1 of 2x plus 7 halves of 4x squared minus 2, you see that that actually is 3 plus 2x plus 14x squared. Right? You've got your 10 minus 7, that's 3. You've got your 2x here, and you've got your 7 halves times 4x squared, which is 14x squared. Okay. So either I was telling the truth, or we were just very lucky.
So is it S is a change of basis matrix?
Yes.
So that's from that to that.
Yes.
Okay, no.
Yes, and so we're seeing an example here. Right. Okay. So you should be curious, right, at this point, right? Why does this S work? Why is this S the right matrix that changes you from one base, the coordinates with respect to the coordinates with respect to another? Okay, so let's explain that. Anybody have questions? Anybody have questions? No? Yes.
I'm a little bit confused
Yeah.
about the matrix that you wrote versus the coefficients for just above, before we did the example. So it's like, for example, the first one is 1 equals, and then the coefficients are 1, 0, 0.
That will give me my first column.
I see, okay.
The 0, 1/2, 0 gives me my second column. The 1/2, 0, 1/4 gives me my third column.
Okay, perfect.
Okay, so you take the coefficients here and you transpose them.
Mhm.
Okay. And that gives you the correct matrix. Okay, so let's come back here and think about how we would get the transition matrix. Okay, so let's start from here, right? We're expressing each of the basis vectors of E as a linear combination of the vectors in F. Okay. Maybe don't use your phone, please. Yeah. Okay. Okay. So let's notate the above briefly as like this: V1, V2 through Vn times S11 dot 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 Sn1 equals W1, etc. Okay, so what I just wrote is an abbreviation of the first line. Okay, right, and we're going to do that for every line. Now, this isn't exactly kosher, right, in the sense that these guys here are not numbers, right? These are not numbers, these are vectors in our abstract space. So, just think of this as an abbreviation for this equation here. Okay. Okay. So altogether, we see that W1 through Wn, if we want to abbreviate all of this, we would write it like this: V1 through Vn times the matrix S11, Sn1, S1n, Sn. Okay, now let's think. If we have the coordinate vector with respect to E, how do we get the coordinate vector with respect to F? If V sub E is some vector x1 through xn, that's the same thing as saying that V is W1 through Wn times x1 through xn. Right? That's like saying that V is expressible as a linear combination of the W's, where these guys are the coordinates. Right? Okay. But we just expressed the W's in terms of the V's. Right? We just expressed the W's in terms of the V's. So I'm going to replace these W's with the V's. Okay, I'm going to use this to switch over to the V's. Okay. So you see that V is V1 to Vn times the S matrix, S11, S1n, Sn1, Snn, times x1 through xn. Okay, which I'm going to rewrite as like this. Okay, it's V1 through Vn times some vector y1 through yn. So we'll call this y1 through yn. So just call it the y vector.
Notice the V is just the coefficients of the original.
Exactly. So these guys are, so what's this? This is the coordinate vector of V with respect to the V basis. Right? When we write something, I know this is kind of dense, but don't worry, slow it down and you can understand it for sure. Okay. So look, when we write something like this, what are we saying? That V is a linear combination of the W's. Right? V is a linear combination of the W's. It is x1 W1 plus x2 W2, blah, 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 xn Wn. Right? These are the coefficients that you use to make a linear combination to get V. Right? Okay. So what's this? This thing here is the expression of V with respect to the E basis. Right? This xi guy. Right? Okay. Now come down here. We've got V equals the VI's times these Y's. So what's that? We've just expressed V as a linear combination of the VI's. So what's this? This thing here is the coordinate vector of V with respect to the F basis. Right? So what's the coordinate vector with respect to the F basis? It's Y. this thing that we call y, which is the S matrix times the coordinate vector with respect to the E basis. Okay, right? The coordinate vector with respect to F is S times the coordinate vector with respect to E, right? In other words, S is the matrix that gets us from the E coordinates to the F coordinates. I know that was pretty complicated. So anybody lost? Anybody lost? Yes, Miko? Good, thank you. Good, yeah. It's very useful to have somebody brave enough to say that made no sense to me. Thank you. Yeah. So I'm just going to say it again more slowly, I'm afraid, okay. So there's two things you got to understand. One is that we've expressed the W's in terms of the V's, right? So that part okay? Right. Every W can be expressed as a linear combination of the V's. Okay. And then we abbreviated that as this thing here. Is that all right?
But was that was the thing that we were supposed to take for granted, right?
No. We
are allowed to know that.
This is this.
Okay.
This is literally this, right? Right. W1 is S11 V1 plus S21 V2 plus et cetera. W2 is blah blah blah. This is just that. Okay. We're not doing anything mysterious here. Okay. And then you say, okay, what does this have to do? How does this help us get the F coordinates? Okay. So you say, okay, well, suppose we have the E coordinates already. That means that V is this linear combination of the W's, right? V, right? Right. What's the coordinate vector with respect to E? It's the coefficients that you would use with the E basis to get V. Right? Is that okay?
I should think of that.
Okay. So yeah, you have to remember what the coordinate vector is, right? Coordinate vector means that you take your vector, you express it as a linear combination of these guys, and you take those coefficients off, right? And that's exactly what this is saying here, right? That if we take xi w1, x2 w2, blah blah blah, then this gives us back v. So this linear combination gives you back v. Okay. And then we use this thing and just substitute for w in order to introduce the v's. Okay. We're trying to move from the E basis to the F basis, right? So we put them in there, okay? And then we see, oh look, this thing here gives us the coefficients that we need to recover V as a linear combination of the VI's, right? So what's this thing here? This is the coordinate vector that we're looking for. Okay. So to get from this to this is just a matter of multiplying by S. Okay. I'm afraid that's the best I can do. Okay. Okay. Yeah. Is everybody all right? Excluding me? Yeah. Okay. Okay. So this is this is how you go in an abstract vector space. Right. This is how you go from one coordinate system to another coordinate system. Okay. Right. It seems a little bit more complicated than what we had to do for the Euclidean space. But if you think about it a little bit, it turns out to be exactly the same. So the book has a slightly different way of saying it. Let me say the book's way. The book's expression of the same information. The book says it like this. The matrix X, the matrix S that we just constructed has the property that Sx equals y if and only if x1 w1 plus x2 w2 plus xn wn equals y1 v1 plus y2 v2 plus yn vn. But if you think about that, that's exactly the same thing. That's actually exactly the same thing, right? Because what this says on the right is that x1 through xn is the coordinate vector of something with respect to E, and y1 through yn is the coordinate vector of the same thing with respect to f. Right. So it's saying that that S takes the coordinate vector with respect to the E basis and changes it to the coordinate vector with respect to the F basis. Let me finish off this section with just a couple of observations about these change of basis matrix. Okay. Which are also called transition matrices. Okay, so first one is that if S is a transition matrix, then it's invertible. If you think about it, well, you think S takes the coordinate vector with respect to some basis and gives you the coordinate vector with respect to another basis. Right? So when could S of something be zero, be the zero vector? What would that tell you if you got the zero vector as the output of S times something? What would that tell you? Well, that would tell you that the coordinate vector with respect to F is the zero vector, right? Well, if the coordinate vector of coordinate vector of V with respect to f is the 0 vector, what vector do you have? It's got to be the 0 vector, right? V has to be the 0 vector, right? Because z is going to be 0 of, 0 of the first guy plus 0 of the second one, blah, blah, blah. That tells you that v is the 0 vector, right? V is the 0 vector. But if z is the 0 vector, then the coordinates vector of v with respect to E is what? The 0 vector, right? The coordinate vector of the 0 vector is going to be the 0 vector, right? Because of the linear independence of your bases. The only way you could get the 0 vector is by taking 0 of the first guy and 0 of the second guy, etc., etc. So by linear independence, this has to be equal to 0, right? Okay. So what does that tell you? That tells you that the only time you can get the 0 vector is if your input is the 0 vector, right? Well, what does that tell you? That S is invertible, right? That S is invertible. So S is invertible. Okay. So if you're a transition matrix, then you're invertible. Okay. And you can probably guess what the inverse matrix is. The inverse matrix is going to be the matrix that goes from the other coordinate system back to your original coordinate system, right? So one way that we could have used Molly's matrix would be to just invert it, and that would have given us the matrix we were looking for, right? In fact, that might be easier, right? Because to get your matrix is a lot easier than to get the other matrix, right? So that's one way to do it. Okay. Part 2, I think I'm going to skip because it's a little bit dense. But if a matrix is invertible, then it is a transition matrix. To some other basis. Okay, so if you start off with one basis, you can use any invertible matrix, and it will get you to some other basis. Okay. I think I'm just gonna skip that because it's a little bit confusing, I think. Okay. But so this gives you another way of thinking about these transition matrices. They're actually all the transition matrices are in fact all the invertible matrices. So transition matrices are just invertible matrices. Each invertible matrix is a change of basis matrix to some other basis. Okay. We've got 4 minutes. That's the end of that. Should we start the next section? Starting the next section doesn't make no sense.
Can I ask a question about
Go
this
ahead.
thing again?
Yeah.
How did the S matrix end up transposed again?
Say it again?
Can you explain how the S matrix ended up with the transpose of those coefficients again?
Yeah. So the reason is that W1 is S11 V1 plus S21 V2 plus SN1 Vn, right? We that gives you this thing here, right? The reason is that when we do this, when we express this thing as a linear combination like this, we're multiplying on the right.
Okay.
We're multiplying on the right. And so if I wrote these guys in the normal order, then I would have to transpose them here.
Okay. Oh,
Yeah.
because it's the row by the column.
Yeah.
Okay.
Yeah. That's the real reason, that this is a right multiplication rather than a left multiplication. Okay, I guess read is save you guys for the next section. Okay, that's enough for today.